today is Rabia Liaquat. She has 8 years of experience in the worlds of mathematics, calculus, algebra, geometry, statistics, mechanics, complex analysis, and graphic theory is the topic that Rabia is going to address for all of us today. The floor is yours. Welcome, Miss Rabia.
Thank you very much. So today I will again explain the topics of graph theory.
And I just wanted to give a special thanks to Ms. Rabia. She's a doctorate candidate, mathematics, bachelor's mathematics, master's degree, and she was able to fill in last minute. As you know, as Dr. Valentine mentioned, we're all human, and Lana, our scheduled presenter, developed a cough and she could barely speak. So fortunately, Rabia was able to join us and fill in for Lana. So we are very, very thankful to Rabia for being able to come in at the last minute and present to us this important topic of graph theory. For those of you who would like to know what exactly graph theory is used for, well, it's basically finding the shortest path in a road or a network. It's, for example, it can be used in logistics, shipping goods from one place to the other. It can be route planning, as on Google Maps, could be the layout of a building, the layout of a store, the layout of a factory. So all of these things are talked about in graph theory. And so that's kind of a summary of what we will discuss today. I see Rabia is trying to share her screen. As soon as she's able to do so, we can start.
Again, we are certainly very, very pleased to have all of you, ladies and gentlemen. You've made the right decision to create some time this Monday. By the way, this is February the 14th, and I want to wish all of you a very, very happy Valentine's Day. No matter whom we are, what we do in life, love is a fundamental element in everything that we do. Of course, we are not very specifically talking right now about all the cases and, no, this is part of it as well, but Valentine's Day is mostly about the type of relationships that we have to sustain with each other. We have Rabia Liaquat back.
Okay.
Let's see.
Rabia, I just did a long introduction for you, so don't worry. We talked about graph theory and the applications in real life, so we're all set up for you to start. So we talked a little bit about the applications.
Okay, thank you so much. So can you listen me and
yes.
See my screen?
Yes.
Okay. Today we will talk about more applications of graph theory. First, we will go towards isomorphism. What is isomorphism? Isomorphism is basically a very general concept that appears in several areas of mathematics. The word derives from the Greek iso means equal and morphosis mean to form or to shape. In other words, we can see isomorphism is a map that preserves sets and relations among elements. Okay, now we will move towards what is isomorphism in graph theory. Two graphs which contain the same number of graph vertices can connect in the same way are said to be isomorphic. What is isomorphic graph example? For example, we have two graphs G1 and G2. Let me draw. Okay. So we have two graphs G1 and G2 are isomorphic. We can say two graphs G1 and G2 are isomorphic if there exists a matching between their vertices, so that two vertices are connected by an edge in G1 if and only if corresponding vertices are connected by an edge in G2. For example, we have two graphs. This is a graph. I named it G1, and also this is a graph. Sorry. This is a graph G2. So I named its vertices 1, 2, 3, and 4. And I named it A, B, C, and D. First of all, we will check the number of vertices. How many vertices of G1? G1 has 1, 2, 3, 4. 4 vertices, and G2 has 1, 2, 3, 4. So G1 and G2 has same vertices, same number of vertices. So next we will move number of edges. How many number of edges of G1 and G2? So G1 has 1, 2, 3, and G2 has 1, 2, 3. 3 edges, same edges. Now we will check the degree sequence. What is the degree sequence of vertex 1 is 1. Degree sequence of vertex 2 is 1, 2. Degree sequence of vertex 3 is 1. And degree sequence of vertex 4 is 2. Anyone can please tell me the degree, what is degree sequence? How can we define degree sequence?
To participate, students, you can go to the reactions smiley face at the bottom of your screen. If you click there, there's an option to raise your hand, and Dr. Valcine will be happy to, or I will be happy to call on you. So far we have no takers, Rabia.
Okay, so let me explain what is degree sequence. For example, we have a vertex 1, and how many edges coming from 1 is 1, only one edge. So degree sequence of vertex 1 is 1. Similarly, for the vertex 2, how many degree sequence of vertex 2? There are 2 edges from 2. One edge is this one, and second edge is this one. So 2 degree sequence of vertex 2. So I write here 2. Similarly, for the third vertex, which has degree sequence 1, because only one edge coming from 3. Similarly, for vertex, there are 2 edges from vertex 4. So I write here degree sequence 2. So this is the degree sequence of G1. Now we will check the degree sequence of G2. How many degree sequence of vertex A is 2? How many degree sequence of vertex B is 1? How many degree sequence of vertex C is 2? Similarly, how many degree sequence of D vertex is 1? So we have a set of degree sequence of graph G1 and G2. We can say there are 2 degree sequence 1 and 2 degree sequence of 2. Similarly, here G2 2 degree sequence 1 and 2 are 2. Both are equivalence. So we can say G1 is equivalence to G2. So number of vertices, number of edges, and degree sequence are equivalent. So we can say G1 is isomorphic to G2. Any question?
Again, we would like to remind every participant, although the last segment of the session will be dedicated to your specific questions, but pretty much like Ms. Rabia just pointed out right now during the presentation, if you have question, you may just go ahead and ask that question. Lakita Sisse, apparently you want to make a comment or question. The floor is yours.
Yeah, thank you, Doctor. Thank you very much to the presenter. So if the sequence here, according to my understanding, is the way in which the number appear. Is that what you refer to as sequence?
Yes.
Yes, please
Yeah.
kindly ask me again. What are you saying about sequence?
The sequence. I'm saying sequence according
Yes.
to what you display here in your presentation. It is the manner in which the number appear. Is this what you define so as sequence?
Okay, we can make a sequence first of all. Let me. So first of all, I will make a sequence like from starting from 1, 2, 3, and 4. Similarly, from the graph A, B, C, and D, I make a sequence of degree sequence. Degree sequence means 1, 2, 1, and 2. This is G1. I make a sequence of degree sequence of vertices. Similarly, for the G2, I make a sequence from A, B, C, and D. 2, 1, 2, 1. Both have the same number of 1. From G1, there are 2 ones, and in G2, there are 2 ones. Similarly, in G1, there are 2 2's, and in G2, there are 2 2's. We cannot worry about the arrangement. We just see the number of 1 is here 2, and number of 1s are here 2. Similarly, the number of 2 are here 2, and number of 2's are there here 2. So we can say G1 is equivalent to G2. If we have a G1, for example, let's say G1 equals to 1, 2, 1, 2, for example, and G2 is equals to 1, 2, 1, 2. Then we can say G1 is equals to G2. In this case, we can say G1 is equivalent to G2. Understand?
I hope the participant does understand the clarification just provided by Ms. Rabia Liaquat. But I believe also Emmanuel Owure has a question. So I'm turning the floor up to you, Emmanuel, for your question. Go ahead, please.
Okay, so I just want to recap on what she said, just to be sure that we are following also in line with what the other participant asked. So is it true that the degree sequence is the number of edges in a vertex? Like the degree sequence of G1 now, that means is the number of edges in all the vertices in a row.
Yes, the degree
Correct.
sequence basically is the number of edges coming from the vertices. For example, 1 is a vertex. There is an edge passing from 1 to 2. From 1 to 2. So degree sequence of 1 is 1. Degree sequence of 2, how many edges? From 2, 1 as this one and 1 as this one. So degree sequence of 2 is 2.
Yes. Okay, that's correct. I think I'm in line. Thanks.
Thank you very much, Rabia and Asuko. now has a question, a follow-up question. Go ahead, please. Asuko, we have lost that participant. Want to remind everybody we are listening and watching Miss Rabia Liaquat in her presentation on the topic of graph theory. Go ahead. Now we have Asuko back. Asuko Herbert, we are listening to you at this time, Asuko.
Thank you, Dr. Franklin. Please, I was also trying to understand that the degree sequence. That is the number, as she has explained it now, the number of edges to a particular voltage. That is the number of lines that forms that point. So I'm clear with it now. Thank you very much.
Thank you very much. We have another question on the chat line, this time from Emmanuel Mawindo, who is asking whether there is a G3 on the example that you are providing, Miss Rabia.
What is the example of?
The question is whether there is a G3 graph in the example that you are providing, or is that possible to have a G3 graph?
Yes, yes, of course. I can draw here G3.
Okay.
For example, this is a G3. Here, for example, I have G3. Let me name it U, V, W, and X. Here we have 4 vertices, 1, 2, 3, 4 vertices. How many edges? 1, 2, and 3 edges. 4 vertices, 3 edges, and degree sequence of U is 1. Degree sequence of V is 2. Degree sequence of X is also 2, and degree sequence of W is 1. So this is also isomorphic to G2.
Wonderful. Right? Thank you very much. I guess you might be able to continue, but I think there are some other questions on the chat line. But before we continue, Ms. Rabia,
yes,
this clarification was provided at the very beginning by my colleague, Dr. Gonzalez. There are students asking whether they are attending the correct session, since yesterday we did announce a presentation by Lana Stawenkovi on the topic of assertive communication, but that precision was again provided at the very beginning today, when the presenter had to cancel last minute because she woke up and didn't feel very well, was sick this morning, couldn't speak at all. And unfortunately, she has to cancel. As soon as that topic is back on the schedule, we will quickly inform our students at Atlantic International University. We certainly apologize for this inconvenience, but we will very soon make up for that presentation. But we have an excellent alternative with Miss Rabia Liaquat, who has volunteered to be a substitute for today, the last minute. And again, she is talking about graph theory. If there is a quest for clarification or better understanding of what the whole topic is all about, graph theory actually is used to find the shortest path in road or in network, we could quickly come up with an example in building design or in factory design or online maps and route planning, multiple locations where the network actually is presented in the form of vertices or persons, objects, or nodes, and the roads are represented as edges, which is what Ms. Rabia Liaquat is emphasizing right now. The roads are represented in the graph theory as edges, and graph theory is used then to find the shortest path between two nodes. Among the questions that you might eventually be interested in asking, we could think of whatever areas or arenas of life that you are evolving in. You could possibly ask the presenter whether graph theory applies in your field. This might be a question that Ngozi has for us or for the presenter at this time. So we are going now to you, Ngozi, for your question or your comment on this topic.
Okay, thank you very much, sir. I understood about the G1 sequence, G2 and G3 sequence. So I want to ask if there is G4 sequencer.
I would assume so, yes. Since we're talking about sequence, we're talking about G1, G2, G3. The question being raised at this time by Ngozi is whether we can have a G4. I would assume so, G4, G5, as long as those graphs apply in the system that you are looking at. But let's go to the expert, Rabia Liaquat. What is your stand on that question, please, Rabia?
So G1 basically a graph connection of anything, G1, G2 and G3. We can go for
Okay.
G4 and so as much as possible, depending on the data, what type of data we have. So we can relate many graphs, many connections according to the data which we required.
I hope or assume, Ngozi, that you are satisfied with
Yes.
response from Rabia. In summary,
Yes, sir.
like what, thank you, Ngozi. What
Thank you, sir.
Rabia, you're very welcome. What Rabia has explained is it all depends on the type of data you are working with. There are
Yes, you're
situations
working
where
with.
only one graph would be involved. There are other instances where you would have two graphs, three graphs, four graphs,
4 and so much,
and
so many.
depending again on the data you are
Type of
working.
data.
All right, thank you for your question, and thank you for your
Thank you, sir.
very precise response, Mr. Rabia. You may continue, Rabia.
Okay.
With presentation.
Okay, thanks. Okay. Conditions of isomorphism in graph theory. So any two graphs will be known as isomorphic if they satisfy the following four conditions. So there will be an equal number of vertices in the graph. So as in the previous, we can see the number of vertices. We check the number of vertices of the graphs. There will be an equal number of edges in the given graph. There will be an equal amount of degree sequence in the given graphs. So, for example, let we talk about the counter example. For example, we have a graph. Now I am going towards the counter example, which are not isomorphic. So 1, 2, 3, 4, 1. So A, B, C, and D. Here, number of vertices are equal. As we can see, 1, 2, 3, 4, 4 vertices, and G2 has 4 vertices. Now we will move towards edges. 1, 2, 3, 4. 1, 2, 3, 3 edges. So 4 edges and 3 edges. So here we can say these are not isomorphic. G1 and G2 are not isomorphic. And the third one is degree sequence. So degree sequence is 2, 2, 2, and 2.
1,
1, 2. Here is 2 degree sequence and here is 1. So here we can see number of edges and degree sequence of both graphs are not same, but vertices are same. But we can say these are not isomorphic graph. Not isomorphic, right? So these are the conditions. These are the main 3 conditions: number of vertices, number of edges, and degree sequence should be the same of graphs. So we can say these are. Okay, next. Okay, these are the graph. Let me zoom it. Here is an example. We can prove or disprove that these are isomorphic or not. So here number of vertices A, B, C, D, E, F, G, and H. How many vertices? 1, 2, 3, 4, 5, 6, 7, 8. Number of vertices are 8. Here,
You may go ahead and continue, Ms. Rabia. We would like to ask all our participants to please turn off your microphones, keep them muted if you are not speaking at any given moment, so that the presenter can continue with her presentation on the topic of graph theory. Sorry for the interruption, Ms. Rabia. You may continue, please.
no problem. Here we can say G1 and G2. So there are 1, 2, 3, 4, 5, 6, 7, and 8. 8 vertices. Both have same vertices. Number of edges. How many number of edges? 1, 2, 3, 4. 4 plus 1, 2, 3, 4. We can add them. So C 1, 2, 3, 4. D has 1, 2, 3, 4. E has 4. F has 1, 2, 3, 4. G has 1, 2, 3, 4 edges. And H has 1, 2, 3, 4 edges. Similarly, we can calculate here 1, 2, 3, 4. 1, 2, 3, 4. Everyone has 4 edges. So degree sequence, number of edges, number of vertices are same. So we can say though both graphs are isomorphic, right? So next I will go for this one.
Sorry to interrupt again, Ms.
Yes, yes.
Rabia. There is a question from Lamine Camara. Does the sequence number work in all graphs?
Yes, every graph has a degree sequence if they have vertices and edges. So this is 100% sure they have a degree sequence. So every graph has a degree sequence if they have vertices and edges. So if there is no any edge, then we can say it has degree sequence 0.
All right, thank you. You may proceed, please.
Yes, of course.
Also for students who are asking if there is going to be a transcript of this presentation, the answer is yes. All the class sessions, all the live sessions are recorded pretty much like right now at this time. And those recordings will be made available to students. And all you have to do is double check every day in the next few days to see if the recording is there on your student portal. It will be at some point. I cannot personally anticipate exactly whether this is gonna happen tomorrow or Thursday, Friday, I don't know. But yes, the Department of Technology is taking all the steps to grab the content from this recording and do some editing if necessary, and then put the recording on your student portal. It will be there very, very shortly. Thank you again for your understanding on this issue. Go ahead, Miss Rabia.
Okay, so the another way to find the isomorphism of two graphs are matrix representation. What is matrix representation? Here are 1, 2, 3, 4, 5, and 6. 6 vertices. B1 has six vertices, and B2 has 1, 2, 3, 4, 5, and 6 vertices. So we check these are isomorphic or not isomorphic. We will check here in matrix form. First of all, how many vertices? 6 vertices. We will write here v1, v2, v3, v4, v5, v6, and similarly v1, v2, v3, v4, v5, and v6. Six vertices. So first of all, we will check the number of edges from vertex 1 to 1. So 1 to 1 has always zero edge. So v1 to v1 vertex has 0 edge. v1 to v2 vertex has 0 edge. There is no any edge. So here we can put 0. So v1 vertex has v3 edge, no edge. So 0. v1 has no vertex with v4. Sorry. v4, so 0. v1 vertex with v5. So there is one edge. See one edge of between 1 and 5. So here we can write 1, right? And there is no any vertex between 1 and 6. So we can write here 0. Similarly, we can check v2. V2 vertex is this one. This one is v2 vertex. So there is no any edge between v1 and v2. So this is v1. There is no any edge between v1 and v2, so we put 0, and every vertex with itself vertex has 0 edge. So I put v2 to v2 is 0, and v2 has no edge with v3, so 0. V2 has no vertex with v4, so 0, and v2 vertex has no any edge with v5 and v6, so 0, 0. Now we will move towards v3. Vertex v3, how many edges of vertex v3 with v1? No edge with v2, no edge with v3. No, there is one edge between v3 and v4. So v4 and v3 with v4 has one vertex, so one edge. So here I put 1. So v3 has one vertex, one edge with v5. So I put 1. v6 no edge between v3 and v6. So put 0. Similarly, we can make every edge like this one and write in matrix form. Similarly, we check v5 and v6. So here is a matrix. Now in the next graph, I will also draw a matrix. So v1, v2, v3, v4, v5, and v6. And we will check with v1 with v1, v1 with v2, v1 with v3, And similarly, we will check all edges from vertex to vertex. So at the end, we get this graph and this graph. So C0 0 0 0 1 0 0 0 0 0 1 0, and similarly all elements are same, so we can say B1 and B2 are isomorphic. Here is another way of finding isomorphism of two graphs B1 and B2. Understand or not? The first one method is we will calculate the number of vertices, number of edges, and degree sequence. In the second one, we can make a matrix and compare both matrices. If they are same equal, then we can say both graphs are isomorphic. And if they are not same, then we can say the both graphs are not isomorphic. For example, we here is an edge between 1 and 2. Then 1 with 2, here will be 1, and 2 with 1, here will be 1. So both will be not isomorphic if there is any edge between 1 and 2. But in our case, both are isomorphic. Understand? If there is any query, kindly ask.
Yes, I noticed that Tangavel Kupen had his hand up a short while ago. I don't know, Tangavel, if you want to eventually ask a question, we would like to invite you to grab the floor at this time to ask your question. Tangavel Kupen.
Yes, hi, thank you, sir. I want to know how these isomorphic graph be useful in our job.
That's a great question. I thought Rabia agrees with me.
What kind of job you are? What kind of job you are doing?
I'm a teacher, maths teacher.
Maths teacher. Okay. So this can, if you are a math teacher, computer science in image processing, these have lots of applications in the field of teaching. Like in computer science, you can image processing, protein structure, computer information system, chemical bond structure. Either two chemical bonds are isomorphic or not isomorphic, social networks, etc. So if you are math teacher, and then you can teach these types of topic. Isomorphism is basically connected every two topics which are same, but which have same representation, which are equivalent. So you can teach in mathematics as well, isomorphic topic.
Thank you.
Okay, thank you very much. I hope you understand the point being made by Rabia Tangavel.
Yes, I want to know in which job we can use this.
You can use it in the field of factories of medicines. So you can check the reactions between chemicals. These are isomorphic to one reaction. For example, we have two medicines, but the patterns are same, the functions are same. For example, Panadol and the second one is Nubrafort. If both have the same structure for the use of fever, for the use of fever, so you should know they have isomorphic structure.
Okay, thank you.
Thank you very much, Rabia. I want to quickly intervene here and bring up a topic, an issue, a theme, which might relate very closely to what you are saying, Ms. Rabia. So far, I assume, or I hope, all our participants are clear on mindful of what isomorphism is all about. Of course, regardless of the fields that they are in, we all directly or indirectly work with data, and isomorphism would apply to the way we are handling or understanding the data when we apply the world of science of graph theory. However, the point I'm trying to raise at this time to make sure every participant is clear about the extent that this information applies to their field. Let's say, Ms. Rabia, that graphs 2, 3, 4, or any number, the graphs are not they're not isomorphic.
Yes.
What are the implications? What would that mean for us, the average citizen, the average person? We're working with graphs in our fields, and we notice to whatever extent that the graphs are not isomorphic. What does that mean? What are the implications, Ms. Rabia?
Okay.
As we are waiting for Ms. Rabia, Sasio Edun Gema, get ready for your question. Let's see how Ms. Liaquat addresses the point that I just made. Then we will turn the floor to you, Acacio.
So if graphs are not isomorphic, I mean non-isomorphic, not having the same form and is used in many branches of mathematics. It is used in many branches of mathematics, identify mathematical objects which are structurally distinct. So we can say if these are not isomorphic, if two graphs are not isomorphic, if two medicines are not isomorphic, then we can say these are structurally distinct. They have their own properties. So this is a unique one from the this medicine, from this graph. So even if two persons have same qualities, so we can say both persons are in other words, if two persons have same behavior, then we can say both are isomorphic. But if they are different from each other, so we can say they have this person has its own properties, this person has its own behavior. So we can relate like this.
Okay, thank you very much. I do understand that pretty much like Ms. Rabia just explained, isomorphism has its way to be applied in virtually all fields of life, all walks of life. When you compare two types of behaviors, we compare two systems, we compare two buildings, and so forth and so on. There is a way to successfully apply science of isomorphism, graph theory. What do you think, Acacio Edun Guema? Like I announced, we are with you at this time. Go ahead.
Hello.
Yes, we can hear you now.
Okay. Good evening, Seth. Thank you for giving me this opportunity to share my idea with you. These topics have very really impact with my job, because I remember in 2013 I have to program an advanced Excel so an application like this to connect two sections, accounting section and statistics section, to discover the possible error that may be coming when we are working and when we are input the data in the computer. That means, for example, as a financial department, when you make that kind of programmation, is very useful to compare the data to realize that, for example, if there are some error when you work, that facilitates us to discover in few minutes or in few time where you can find the possible error, how we can resolve the problem, how we can discover from where the error have been coming. That's the single idea I can share with you. And that helped me very, very, very well when I've been working in accounting section. Why? Because when I try to input the data, for example, the account is different from the budgetary law. Budgetary law. I would like that the mistake may come from me or from the book or from the person who makes the financial statement. That is all.
Thank you for your question,
Okay.
Acacio. How do we assess error when we work in that field of graph theory, when there is an issue about the way we understand isomorphism? Before you tackle the topic, the segment of graph coloring, if you have a stand on this question raised by Acacio, Ms. Rabia, we would like to hear from you, please.
So basically, your question is if where come from the error in the accountings? So basically, in accountings, you have not the exact number. You can approach in accounting statistics. You can approach that number because the data is very high, big data. So you can approach the exact results. So there is a minor error. At the end, we can calculate the actual and error result, and you can see the how much error is coming.
Thank you very much, Rabia. You may continue now on the segment of graph coloring, please.
Yes. Graph coloring. A graph coloring is an assignment of labels called colors to the vertices of a graph such that no two adjacent vertices share the same color. The chromatic number denoted by x of g of a graph G is the minimal number of colors for which such an assignment is possible. Let's suppose this is actually a labeling of graphs vertices such that no two adjacent. What is adjacent vertices? For example, we have a graph A, B, and C. We have a graph A, B, and C. So A has adjacent vertices are B and C. A is adjacent to B and C. B is adjacent to A, not with C, because both have no any edge. So C has adjacent with A. B and C are not adjacent. So in here we can see two adjacent vertices should have different colors in graph coloring. Next we will move. Graph coloring problem is assigned to colors to certain elements of a graph subject to certain constraints. Vertex coloring is the most common graph coloring problem. The problem is given m colors, find a way of coloring the vertices of a graph such that no two adjacent vertices are colored using some color. The other graph coloring problems like edge coloring, no vertex is incident to two edges of same color, and face coloring, geographical map coloring can be transferred formed into vertex coloring. Here three things are vertex coloring, edge coloring, and face coloring. Everyone known about vertex and edge. What is face? Face is just like this one. For example, this is a face. This is a vertex, this is edge, and this is a face. So here we can talk about vertex coloring, that two adjacent vertices should be unique colored. For example, this is a graph. So if we have a red color here, then the other vertices which are adjacent to red should be not red color. So I will color it with blue. Here we can see every vertex has unique color from two adjacent vertices has unique color. For example, A, B, and C. A and C are adjacent but different color. A and B are adjacent vertices but different colors. So chromatic number of G, let's suppose G, chromatic number of G equals to, what is chromatic number? Chromatic number is minimum number of colors which can cover a graph without any repetition of color between adjacent vertices. So chromatic number of G is 2, right? And now I have another graph. I will talk about edge coloring. Same concept as it is vertex coloring. So here two edges which share a same vertex should not be the same color. For example, I have a color of this one is red. For example, this is a red. So the adjacent edges are this one. This is an adjacent vertices, adjacent edge with AH. Let I write A. So both are not red. So I mark them with blue. Right? So this one should not be blue. I can color it as red. So here I can we can say that edges which are adjacent to each other should be different colors. So this is called edge labeling, edge coloring. Similarly, a face color. How can I draw a face coloring? Let me draw a face. Let me draw a cube. Sorry. This is a cube. imagine this is a room. Room has upper and lower. So, for example, we have one face. This is a one face. The adjacent faces, the other one adjacent faces with this face is back side. This one face, and this one face. These are adjacent to upper one face. So these three should not be red. So we can color it like yellow. So the adjacent faces of yellow are this one face, this one face, and this one face. So I will choose the color blue for this one face and this one face. Right? So I will choose the same red color for the this one. This is a face coloring. And I can also choose the yellow color for the front face. So the total chromatic number for face coloring is 4. Of face. Is 4 for a face, for cube. I hope you understand the cube coloring, sorry, face coloring, vertex coloring, and edge coloring. Right? Means two vertices which are adjacent have not similar color. Similarly, edge coloring, two adjacent edges should not have the same color. Similarly, the same concept for the face coloring, where two faces which are adjacent to each other have different colors. So these are the concept of vertex coloring, edge coloring, and face coloring. Next chromatic number are the smallest number of colors needed to color a graph. G is called its chromatic number. For example, the following can be minimum color of 2 colors. So minimum color required to color edges are 2. So chromatic number is 2. Here chromatic number is 4, and the and the vertex coloring minimum numbers are 2. So chromatic number of vertex coloring are 2, and face coloring is 4. So these are the examples of graph coloring, where vertex coloring, edge coloring, and face coloring. This is also an example of chromatic number. For example, we have a cube, square, and we want to color its vertices. So if we color it red, next adjacent vertices are these one. For example, A, B, C, and D. So A, B, C, and D, if we color B and C, should not be red, because the adjacent vertex A is red, so we color it blue, and the fourth one vertex should not be colored green, because adjacent vertices C and B are colored with green, so we color it red. So chromatic number is 2, right? So chromatic number of this graph is 2 because in this above diagram we can use two colors, red and green. So chromatic number of this graph is 2 and is denoted by x of g, means x of g is equals to 2. Chromatic number defined as the least number of colors needed for coloring graph, and types of chromatic number are cycle graph, planar graph, complete graph, bipartite graph, and trees graph. Next I will it means chromatic numbers are belongs to these types of graph. We can coloring these types of graph: cycle graph, planar graph, complete, bipartite, and trees. What are these types of graph? What is cycle graph? First of all, cycle graph is a graph if we start from A, move towards this one to B, and then back to A. I mean first and last points are same, then this is a cycle graph. For example, this is a circle, starting and ending point are same, so this is cycle graph. So next is planar graph. So planar graph is those graph which where two edges cannot cross to each other. For example, this is a planar graph and this is non-planar graph, because two edges are cross to each other. Two edges are intersect each other, so this is non-planar, and this is a planar graph where no two edges are intersect, right? Next one is complete graph. For example, we have 1, 2, and 3, and 4 vertices. So A, B, C, D. Complete graph says that A should be every vertex should be connect to any other vertices. For example, A should be connect with B, A should be connect to D, A should be connect to C. Similarly, for the same thing for B, B should be connect A, B should be connect with D, B should be connect to C. And B connect to A, D connect to B, D connect to C. And C connect to A, C connect to B, C connect to D. So every vertex are connecting with each other vertices. So this is a complete graph. Similarly, bipartite graph. What is bipartite graph? A bipartite graph is a set of graph vertices decomposed or split into two disjoint. Disjoints means, for example, this is a graph. Disjoint part is non-common area. For example, this is a common area, and the disjoint part of this one is this area. This area and this area are disjoint, right? So disjoint sets such that no two graph vertices within the same set are adjacent. For example, here is the example of bipartite graph. Here we split vertices into two sets where 1, 2, 3, 4, 5 and A, B, C, and D. These are the two disjoint sets. So here is bipartite property has that within the vertices of one set should not be adjacent. For example, 1 should not be adjacent to 2 because there is no any edge between 1 and 2. 2 and 3 are not adjacent. 3 and 4, 4 and 5. So this is a non-adjacent set of vertices with itself set, right? So bipartite graph said us 1 should be connect with A, should be connect with B, C, E, but not connect with 2, 3, 4, and 5. This is a bipartite graph. So this is another example of bipartite graph. For example, we have a graph A, B, C, and D. So this is a square. We can make a bipartite graph here. We split this into two sets, A and B, and C and D, right? A, B, C, and D, and connect with opposite vertices. A connect with D, and so this is sorry, we split in this way, not A, B, C, D. We split it AC and BC, BD. Splits into two sets, AC and BD. So A is connect with B, A is connect with D, C is connect with B, C is connect with D. But A and C, B and D, these will not be connect with each other. So this is a bipartite graph. And trees. What is trees? Trees are simple a path where no cycle, no multiple edges,
I'm so sorry to interrupt and
Yes.
make a point real quick at this time, Miss
Yes.
Liaquat.
Yes.
We are about to run out of time since we had actually 1 hour allotted
Yes.
for this session, but there is a question that just popped up on the chat line from Lamine Camara. Where can we apply graphs coloring in our works, in our line of work?
These are the applications. Making schedule or timetable. For example, in the schedule or timetable, we want there will be no any intersection between two persons timetable. So making schedule and timetable, we use coloring graph. So in the schedule of time schedule or timetable making, we use coloring graph. Mobile radio frequency assignments. In the you can study here, when frequencies are to towers, frequencies assigned to all towers at the same location must be different. How to assign frequencies with this constraint? What is the minimum number of frequencies? Here coloring are resemblance with frequencies. Frequencies needed. This problem is also an instance of graph coloring problem where every tower represents a vertex and edge between two towers represents that they are in range of each other. In the Sudoku games, also variation of graph coloring problem where every cell represents a vertex. There is an edge between two vertices of the vertices if they are in same row or same column or same block. For example, this is the Sudoku game. Right? Wait, I can. So Sudoku game, we want every block should be a unique number. For example, 1, 2, 3, 4. Unique row. So we allot one red color with blue second color, yellow third color, and fourth one is black color. So we allot colors in Sudoku games to representation unique numbers in every block. So here solving Sudoku puzzles, we can use graph coloring. This is another example of graph coloring where we used colors, different colors, and here if we choose red color, then next one should be different from red. So here I choose blue color, then yellow color, then black color, and here we will apply 1, 2, 3, 4. Similarly, in the fifth position, I will take yellow color, which is 3. Fifth position, 1, 2, 3, 4, 5. In fifth position, I allot yellow color. So here put 3. In sixth position, I allot black color, which is 4. So I put 4. In seventh color, which is red, so I put 1. And similarly, in eighth position, I choose blue color, which is 2. So I put 2. Similarly, in this way, we can solve Sudoku puzzles with the help of graph coloring. Right? Similarly, this is another application of map coloring. Geographical maps of countries or states where no two adjacent cities cannot be assigned same color. 4 colors are sufficient to color any map. Right? So we can say the coloring problem has a huge number of applications in modern computer science, such as making schedule of timetable, Sudoku, bipartite graphs, map coloring, data mining, networking, final exam, timetabling, aircraft scheduling, guarding, and art gallery. Here is the So this is also an example of chromatic number. These are few graphs where I allot numbers, colors, and chromatic numbers. You can see here. So any question in the whole lecture, kindly ask me. Today's lecture is over. Any question?
I don't see any hand up at this particular time, so you may wrap up the session since the recording again will be on the students sections very soon.
So I also shared this presentation with you guys.
For participants who have again raised that question as to what's going to happen for those who missed some key points in this presentation by Rabia Liaquat. Remember, today or every other single day for our live class sessions, the entire recording will be put in your student portal for you to see and read and download, do whatever you please with it. So don't worry about being late. Of course, we wish that everybody be on time, but if humanly speaking, it happens to you to report late for this session or any other session in the future, please don't worry about it, since shortly after the class, the recording will be right there on your student portal. Your conclusion now, please, Miss Rabia Liaquat.
So today we discuss about 2 topics, isomorphism and graph coloring, and there are its application on applications. So with these 2 topics, I end up the classes. And today I really enjoyed to deliver my lectures. Thank you so much.
Thank you very much. I think this was again another outstanding presentation by a member of the family of Atlantic International University. You have played your role outstandingly, Miss Rabia Liaquat, and I am convinced that every other participant is of that idea that your presentation was really worth it from every single perspective. Those types of technical information, they are not available anywhere. We don't even have books about them, so we shall consider ourselves very blessed to be part of that family and enjoy this type of presentation. I apologize again for those of you who were late. I also want to remind you the topic that was initially scheduled for today was assertive communication, but the presenter, Lana Stamenkovi, could not make it because of a health issue that popped up in the last minute. But we were fortunate, very blessed indeed, to have had Miss Rabia Liaquat who filled in very, very wonderfully. We thank everybody, every participant, every student, every member of the AIU family who joined us for this session. And please don't forget that recording is not lost. If you missed anything, it is going to be in your student section after the technology department makes the necessary adjustment to place that recording in your student portal. Thank you very much again, Miss Rabia Liaquat. You've been really great, quite awesome indeed. Thank you, everybody. It's been a real pleasure having you today. And remember, it's every day, Monday through Friday at 10 o'clock in the same channel for our live class sessions. Thank you very much again. And everybody, please have a blessed day. Bye-bye now.